constraints. So this is a small demo. So now we have this is for attack against cookie system by the homemade detector. But what about the commercial detectors? Seba will continue to present this.
Okay, so what I would like to present, to finish with, is illustration of control with this time an actively quenched detector. So a detector for which the avalanche is quenched actively. And this is a commercial model which is manufactured by Perkin-Elmer. That's the mostly used commercial single photon detectors at those wavelengths, so working with QKD systems in the visible or in the infrared. Yes?
Actively quenched, what does it actually mean?
That means that when you have an avalanche, you need to quench the avalanche. You need to lower the bias voltage of the diode below breakdown to quench the avalanche. And it can be done passively, as you saw on the first detector, or it can be done actively, like with this detector with some electronics. And you can see here simplified circuit diagram of the detector. So he takes a bit of reverse engineering for those detectors. And well, maybe I can try to get there. So you can see the APD here. And on the right part, you have basically the comparator, which senses the onset of the avalanche. And then you have the quenching circuit. Basically, what the quenching circuit does is that after 14 nanoseconds, it connects the anode of the APD to plus 30 volts. So it quickly reduces the voltage difference at which the APD is biased. So it quenches this way actively the avalanche. And 20 nanoseconds later, there's also a reset circuit. So that's the quenching part of the circuit. And here you go into what you have here actually is the power supply, which biases the APD at about 350 volts. To go back. Okay, and what Eve does in that case, again, the strategy is to blind the detector, to bring him to work from Geiger mode to linear mode in which the detector is blind to single photons. And in the previous case, you saw that Eve was using CW, bright illumination. In that case, what we use to control the detector is pulsed illumination. But basically, that's the only detector-dependent difference. So Eve applies here bright pulse, typically 50 nanosecond wide, above 2 milliwatt optical power, so much above single photon level. So, and here the current goes pretty much. And you have here a current limiting circuit, which kicks in when the current goes above 10 milliamps. And the current is drawn into this decoupling capacitor, C9. And here you have the output of an operational amplifier. And this operational amplifier is pretty slow, and the output is overloaded by the current here. So as a result, the operational amplifier outputs deeps, typically few volt deeps, signal onto this FET transistor. And this transistor actually controls the power supply which bias the APD here. And when the Eve sends bright pulses of frequency typically over 70 kilohertz, the power supply gets disrupted by the 1 volt deeps signal output by the operational amplifier. And usually the power supply phase locks to the frequency of the perturbation. And as you can see on the next picture, the detector gets under control. So what the picture shows actually here is the monitoring the bias voltage at the APD as a function of the frequency of the bright pulses that Eve is sending. So under normal operation, the bias voltage is around 350 volts. And as you can see, when Eve applies a pulse of increasing frequency, the bias voltage drops. And when it drops by more than 12, 14 volts, typically, the detector gets completely blind to a single photon. And that corresponds to the field squares and dots and so on. So here you have a regime where the detector gets under complete control under bright illumination. You can see on the right part of the figure that there's another region where you can control the detector. And surprisingly, the bias voltage is back to the nominal value. So you could say, hey, how can you control the detector here when the bias voltage is, again, around or above breakdown voltage? It should work again as in Geiger mode. And the assumed reason for that is the following. When you apply very bright illumination, you start to heat the APD chip. And one known feature of heating is that it will raise the breakdown voltage of the APD. Because before, you have a set breakdown voltage, and you bring the bias voltage below breakdown, and then the detector is blind. But under bright illumination, you can see that the bias voltage is back into nominal value. But what the heating produces is that it rises the breakdown voltage. So again, the diodes end up below breakdown, and you get it under control. What you see here is oscillograms of the detector output as a function of optical illumination. So here you have the bright pulses that Eve sends, and you can see that, of course, those bright pulses triggers a click at the detector, but between two clicks, the detector is completely blind. Now, if here you apply a pulse of sufficient intensity, then you get controllably the detector to click with unity probability and very low sub-nanosecond time jitter. So you get the detector under complete control again. And then we return to the fake state generator.
Quick question.
Yes?
Quick question about the heating effect. Have you devised any experiment to check whether that is actually heating or not? For example, walking very, very slowly through the various frequencies that you're showing, it struck me that the variable that in your plot seemed to be characteristic for the transition between regime 2 and 3 was really the
Hello?
pulse frequency and not the and not anything else.
Yeah, you're right. I mean, the question was whether we had assessed that this transition from one region to the other was actually caused by heating of the APD. And at this point, it's an assumption that we have to check. What we know is that a known cause of rising of the breakdown voltage is heating, and I mean, we thought that it could be an explanation, but that still needs to be checked. Okay, so we're back to the fake state generator, and basically what should be reminded in this presentation is that somehow what you need to control the crypto systems equipped with Avalanche photodiode is a control generator to blind the detector. And as you can see, depending on the detector, sometimes you will blind it by using CW elimination, sometimes by using pulsed illumination. The idea is to bring the bias voltage of the APD